very good. So first of all, welcome everyone to this junior session of the webinar Control and Time of Crisis. So today we'll have two speakers. So the first one will be Armand Koenig from Dauphine University in Paris, and he will talk about null controllability of parabolic transport systems. So please, Armand.
Okay, thank you, Sylvain. Thank you, everyone, for coming here. And yeah, I'll talk about null controllability of parabolic transport systems. So you all know this, but just to fix the notations and the terminology, we say that an equation, for instance, here, the heat equation, is null controllable on small omega and in time t if for every initial condition there exists a function u which is supported on 0t times small omega, such that the solution of the heat equation with our control u on the right hand side is 0 everywhere at time capital T. And you know that as long as the domain on which the equation is posed is connected, bounded, and smooth enough, then the equation is null controllable on any non-empty open subset. Actually, we don't have to ask open. Omega can be measurable with positive measure. Anyway, the equation I will consider here, and by the way, it is a collaboration with Kevin Lebalch and Karin Bochard. The equation are parabolic transport systems that are written in matrix form. F is a vector as dtf plus a matrix, dxf minus b dx square f plus some zero order term, and plus a control here. And we will work only with X in the one-dimensional towers, or if you prefer, sorry? Okay. We will ask X with a periodic boundary condition. So the hypotheses on the matrix A and B are that B can be written in block form as 0, 0, 0, D. With D plus D star, we will ask it to be positive definite. And if we write the analogous block decomposition of A, we'll ask that the uppermost leftmost block, A11, to be Hermitian. Actually, we have a slightly more general hypothesis, but this is just basically nothing. I think we didn't write it this way, but I think we could have always use this form and generalize to our hypothesis, but whatever. I will work under this hypothesis. Why do I say that this is a parabolic transport system? That's because if we write this equation explicitly in this block form, so on this component, we will have no dx squared here, we have no b. So this is dt plus a1. So do you see my my pointer? Because I think I lost it. No?
Yes, perfect.
Okay, perfect. Sorry. There's a small bug on my side. Okay, so on this component, we have dt plus a11 dx plus the zero order term, and we have no dx squared. So this is a transport equation on fh with coupling from the other component. And on this component, we have dt minus d dx squared plus lower order terms and coupling from the other components. So we have here a parabolic equation and here a transport equation. And the question, as I said, is this system null controllable? On what time? And what if we ask for the control UH here, for this component of the control, what if we ask them to be 0? And what if we ask this component to be 0? Okay, so the results. The first and main one is, so we ask for simplicity that the control domain is an interval, an open interval. And we define this time capital T star to be 2 pi minus the length of the control interval, divided by the smallest in absolute value of the eigenvalue of the A11 matrix. So let's recall that A11 is the matrix before the dx in the transport components. And by the way, 2 pi is the length of the one-dimensional torus, right? So with this capital T star defined, then the system is not null controllable on omega in time less than T star, and it is null controllable in times greater than T star. Just a quick remark is that this T star is actually, this minimal time is the same as this transport equation. So basically on the previous equation, you keep only the transport equation, you forget the coupling, and well, the zero order term doesn't change anything actually, but whatever. And then this transport equation has a minimal time of null controllability, right? Because the free solution are sums of waves that travels at the speed given by the matrix A11. So if you want to control it, you have to wait that these waves go everywhere in the domain. And this minimal time for this transport equation is this one. And it's not a coincidence. We will see that it's actually, it comes like that in the proof. Okay, so now what if we ask for this control here to be 0? Well, we basically have null controllability in the same time, but now we have to, for null controllability, we need a Kalman-Roem condition between this matrix A21 and A22. Right. We have to, because if you see this dxfh to be a control, an indirect control, that's what's happening, then you need a Kalman condition between these two matrices. And if you have the Kalman condition, you have null controllability. And well, also, by the way, I forgot that in this case, we ask to not to have a zero order terms, because it would be basically intractable with this zero order term. Well, we wouldn't have a nice enough condition, actually. And also, we ask for the diffusion matrix to be the identity. And now, if we ask for the parabolic control, sorry, for the hyperbolic control to be 0, and we want to control only the parabolic components, we have a similar situation. So we need a Kalman-Roem condition between the coupling matrix and the matrix of the system, the matrix of the transport system. And in addition to this Kalman-Roem condition, we need also a regularity condition on the initial condition. We can control only initial conditions that are regular enough. By the way, this regularity assumption is too strong, but that's what we prove with our methods. Okay, so before going to the proof, let's give an example of an actual equation that are actually studied by people where that is an example of a parabolic transport system, and I'll use the linearized compressible Navier-Stokes equation. So Navier-Stokes equations, right? We have the equation, the conservation of mass, dt rho plus dx rho v equals the control. So by the way, rho is the density of the fluid, and v is the velocity field of the fluid, and a, gamma, and mu are just constants. And now the Newton-like equations, dt plus dt, rho plus dtv plus v dxv plus, so here basically we took a special law for the pressure. For instance, it could be an ideal gas. And minus the velocity part, mu dx square v equals the control. And so this is a nonlinear equation, right? And we look at the linearization around a stationary state, that is a state rho bar, v bar, which are just numbers. So basically, it's just a thing that turns always with the same speed. And the linearization, then we have dt rho plus v bar dx rho plus, rho bar dx v. And for the other equation, dtv plus v bar dxv plus something coming from the pressure minus mu over rho dx square v. And you see that it is a parabolic transport system, because here we have a transport equation here, a coupling here, and here we have with this term here and this term here, a parabolic equation with a coupling here. Okay. So, of course, we are not the first one to study the Navier-Stokes equation, and there are actually a lot of articles. I'll just give two, but there are much more, and I'll just focus on wide-dimensional case. But there are also articles on the two-dimensional or more, or in more dimension. So one of them would be by Hervé Deza, Guerrero, Glaspuel in 2012. So they didn't consider periodic boundary conditions. They considered the equation posed on an interval, and they didn't take internal control like that. They took boundary control. But with two boundary control, one of them acting on the density, one of them acting on the velocity, they managed to prove the null controllability in times bigger than the length of the interval over the velocity. Actually, they didn't study, they didn't write the article on the linearized equations. They treated the actual nonlinear equation, the local controllability of the nonlinear equation, but in there is the linearized equations that happens. And another equation, another article. There are actually a lot of articles with these people. I'll just took one. I think it's one of their best results in the wide dimensional case. So with only one control acting on the velocity, they managed to prove the null controllability in terms greater than 2 pi over absolute value of V bar for the initial conditions that have the density that is H1. Now, with our general theorem before, if we try to apply this theorem, then the matrix A would be this one. So we have V bar and other things that don't matter. And B would be 0, 0, 0, and mu over rho here. So if we try to put only one control on the velocity, we managed, this theorem gives us the null controllability in times bigger than 2 pi minus the length of omega over absolute value of V bar. So slightly smaller minimal time of null controllability. But with the initial condition, we need a stronger regularity assumption on the initial conditions. So apart from this, which is a bit stronger, we get basically the same results. And this is true for the other case of parabolic transport equation that happens. There are several of them. We have heat equation with memory. We have wave equation with structural damping that can be written as a parabolic transport systems, and we basically get the same results as the existing article. Okay. So now let's talk about the proof. Well, the idea of the proof, because the article is, I think, 60 pages long, so I won't go through all that, but let's just give the basic idea, because if you can keep the basic idea in mind, everything is just really simple techniques. It should go really easy. So the first thing is we try to see in the equation something that looks like a parabolic equation and something that looks like a transport equation. So that this kind of thing also happens in every article that deals with parabolic, with special scale or special cases of parabolic transport systems. So we'll use a Fourier series, of course, because we have 2p periodic boundary condition and constant coefficient. So this operator, and by the way, I'll also forget about the zero-order terms because it would just add some terms sometimes, but it really doesn't change anything. So this operator minus b dx squared plus a dx in the Fourier side, it acts as, n squared b plus in a, right? And I write it this way because we see that what happens when the frequency is large enough, it's just a perturbation of the matrix B. Okay, so the spectrum of our operator is just n squared times the spectrum of this matrix. And now we will use the perturbation theory, and we see that the eigenvalue of B plus I over NA, when n tends to infinity, this eigenvalue converges two eigenvalues of the matrix B. So there are two cases. If this eigenvalue is not zero, then n squared lambda nk, so basically the eigenvalue of this operator, they look like n squared lambda k. So that looks like the spectrum of a parabolic operator. But if lambda k is equal to 0, then this eigenvalue we have to look for the next order in the asymptotic expansion of this eigenvalue, and then this eigenvalue n squared lambda nk look like in lambda mu k, and that's something that looks like the spectrum of a hyperbolic operator. So we call them parabolic frequencies and hyperbolic frequencies. So there are two things that we can say already. Is that since the free solution, so we write them along this component, so these are the sum of x nk exponential inx minus n squared lambda nkt. That's approximately the sum over the parabolic frequencies of x nk exponential inx minus n squared lambda kt, plus the sum over the hyperbolic frequencies of x nk exponential inx minus in mu kt. And this series can be summed if the real part of lambda k is positive and if mu k is real. So if these two conditions are satisfied, the equation is well posed, which is something I didn't prove before. Okay, but these conditions are ensured by our hypothesis on B and A. And the second thing we can say is that if we look at this sum on the hyperbolic frequencies, this is a sum of things that go at speed mu k, right? So if the time is too small, then we can't have null controllability. Of course, it's a tiny bit annoying to write all of this rigorously because of this approximatively equal. This thing is only valid in high enough frequencies, and we have error terms that we have to deal with, but we can do that. Okay, so now let's talk about how to control actually. So the thing we would like to do is, we know how to control a heat equation. I talked about it really quickly at the start, and we also know how to control a transport equation. I didn't talk about it, but it's pretty easy, right? You just follow the transport. But these two arguments are of really different nature, right? For the parabolic equation, that would be Kalman estimates, maybe, or maybe the Lobo-Robiano strategy. And for transport equation, it's just a propagation along a flow. And putting these two together, we need to be a bit smart. So what we will do is the following thing. We will look at two sub-problems first. The first one is, give me a control UH that acts on 0 and T prime. T prime, you will choose it smaller than T, but just a little smaller. So give me any control UH, and I will try to find a control UP that acts between T prime and T, and that controls only the parabolic frequencies in time T. And on the hyperbolic frequencies, it can do whatever it wants. Second problem, gives me any function UP that acts between T prime and P, and I will try to find a control UH that acts between 0 and T prime, and that controls only the hyperbolic frequencies. And on the parabolic frequencies, it can do anything it wants. All right. Now, imagine that I choose a control UH randomly. If I can do these steps, I'll find a control UP that controls the parabolic frequencies. And now, with this second step, I'll find another control UH that controls the hyperbolic frequencies. If by chance this control UH is the same as the one we started with, then it's over, because we control the parabolic frequencies and the hyperbolic frequencies. Thus, we control everything. So what we will do is that we will force this thing to happening. We will force these loops to land on its feet by by choosing this control UP here smooth enough, and then since the application, the map that gives this control UP is compact, we can use the freedom alternative to make these two steps agree. And well, using the freedom alternative, we lose a finite dimensional space, but we will deal with that later. Okay, so how do we do with these two steps? The first one, well, we have the control UH that does something, whatever. Since we only control the parabolic frequencies, this is a control problem for a parabolic equation in times t minus t prime, and we know how to do it. In the article, we use the Lobo piano strategy. For the second problem, this can look a tiny bit annoying because we have our control, and only after we have the UP that does something that might destroy what we did. But that's not the problem. Because we control only the hyperbolic frequencies, the equation is actually reversible on these frequencies. So, okay, UP does something. It can do anything it wants. Whatever, since the equation is reversible, we reverse the time here, and then we have a new initial condition, and we try to land where we want here. So this is actually an exact controllability of the perturbation of a transport equation in time t prime. So the perturbation, if you have ever worked on the control of hyperbolic equation, you know that a perturbation is never an issue. Okay, and then we have a few finite dimensional space that are left here and there, but we do this with a compactness uniqueness argument. If you have worked on the hyperbolic equation, compactness uniqueness arguments are, you know about them. It can be a little surprising that we can make a compactness uniqueness argument on parabolic equation, but actually at this point we have much stronger results than what we, sorry, how to say that? We arrived at a much better place to do the compactness uniqueness argument than what is usually done in a hyperbolic equation. But I won't detail that. It's like 2 pages of functional analysis. So basically, once we do this, we won, right? Not exactly, because there's a problem I sidestepped. Until now, what I described is nothing really new. It's basically the strategy of Lobo in 1998 for a linear system of thermoelasticity. This is a system that couples a heat equation and a wave equation. And what we did is generalize this method for systems of arbitrary size. And the difficulty is that the eigenvalue of B plus I over NA, the matrix that happens before, well, they can behave pretty badly. Oh, sorry, there's a misprint here. This eigenvalue can behave badly as the frequency goes to infinity. Maybe we have generalized eigenvalue. Maybe the eigenvector, maybe even the generalized eigenvector can behave badly. Maybe if n goes to infinity, the basis of generalized eigenvectors stopped to be a basis as n goes to infinity. So we can't prove this this doesn't happen. And the solution is we just don't use the eigenvalues nor the eigenvectors. What we use is something that is called total eigenprojections. That is a sum of eigenprojections associated to eigenvalues that are close to each other. And the reasons this behaves much nicelier, is that we have this formula. So if M is a matrix and I integrate the resultant of M over some closed complex curve, then this integral is the eigenprojections on eigenspaces associated to the eigenvalues of M that lies inside the path gamma. And you see that once we have this, I can change a bit the matrix. I can perturb the matrix M, and it's not a problem. And there's something else that we use. It's called the reduction process. So basically what I'm saying here is that we are happy that Cato wrote his book, and the thing that we had to do is find in his book the right formula, which took us actually quite a bit of time, but you know, in the end, every time in the previous slide where there was eigenvalue or eigenvectors, you replace that with these total eigenprojections, and it just works. Okay, so just to conclude briefly, it seems that for the control of the parabolic transport system, then we have null controllability if and only if the transport equation is controllable. And it's not a coincidence, as I said, it happens like we see it in the proof. But there are a lot of open problems. One of them is that we have only a theorem with periodic boundary conditions with the one-dimensional torus. What happens if we don't have a one-dimensional torus? What happens if we have a segment? We don't know. What happens if we have an open subset of Rn? What happens if we have a manifold? We don't know. What happens if we have less controls than equations? So we have some partial results, but maybe we can try even more than that. What happens if we have non-constant coefficients? That's also something that looks pretty challenging. And also unique continuation, and there is a lot of open problems. But I'll stop there. Thank you very much.
Thank you, Armand. So I'm uploading in the name of the whole audience, as it is.
Yeah. I think we're used to that by now.
Okay. So are there any questions? Well, if so, please, you can open your microphone and ask. So Jean-Michel, I see you have a question.
Yes, very nice talk. Yes, very interesting. But for example, for the parabolic equation, it's known that you can also have some controllability by acting on some of the components because of the coupling. Is it possible to mix that with what you are doing? That is, let's assume, for example, there is no control on the hyperbolic part, but for the heat equation, you have only some components that you are controlling. Is it possible?
That's a thing that would have to be done. I can't answer it with certainty right now. Yeah, so basically, the thing you would like to do is that you would like to control indirectly the parabolic components that you didn't control at first, and then control doubly indirectly the hyperbolic components. Yeah, that sounds reasonable, but we don't have a proof written yet. That's something we would like to do. Yes.
Thank you.
Are there other questions?
Well, may I ask a question?
Yes, Olivier, please.
Armand, do you think you could deal with source terms on the right side, on the right-hand side? I mean, for the parabolic part, it should decay at final time, but not necessarily on the hyperbolic part. Do you have any idea of the kind of source terms that you could add in the right-hand side?
So maybe I will say something stupid, I don't know, but basically, let's go a bit back. If you can do this at the source term on these two sub problem, I think the proof works. Maybe I'm saying maybe it's a mistake, but I think that if you can have a source term here and here, that you can have a source term in the system also. But I'm not exactly used to this kind of thing, so as I said, maybe I'm wrong, but maybe it's possible, yes.
Okay, of course, what I'm thinking is to go to the nonlinear system afterwards, of course.
Okay. But right, okay. So if you have two controls, at least, since you control any with an L2 control, you can control any L2 conditions. in this case, you can do a simple fixed point argument. But yes, maybe you are thinking about having less control than equation, and then you have some regularity assumption, and this doesn't work. Is this what you are thinking about?
Well, what I was thinking about is what you ask on the parabolic part, because on parabolic part, usually you have to ask that it decays strongly at final time. And is it possible to characterize spectrally how it behaves?
Ah, okay, yeah. That I don't know why. That's not something I know, sorry.
Okay, are there any other question? Well, so maybe I have one. I'd like to better understand at what point you are using that you are on the torus. So for instance, for the hyperbolic part, if I remember correctly, the work by Thibault and Zoisoi, it was on an arbitrary domain, right?
Yes. So what Thibault and Zoisoi did is that so it was a heat equation and a wave equation, right? And the Laplacian is 0-2 equation is the same. It's the same equation on the same Riemannian manifold with the same metric. So they had a common basis of eigenvectors for these two equations. And for transport equation, well, that doesn't happen, right? If you have a segment, you don't have a common basis of eigenvector. But here in the torus, that's where we use it. The reason we have we need a periodic boundary condition is that we have the exponentials that are eigenvalues for the dx squared and for dx also.
Okay. And could you try to shortcut a little bit this spectral approach?
That looks very hard because it's really at the heart of the entire argument. Even in there, we use a lot of projections that are constructed on this spectral analysis.
Because, well, for instance, I remember in our work on compressible Navier-Stokes equations, we were not using spectral estimates. We were using some kind of good variable on which we were able to see to decouple somehow parabolic from hyperbolic effects.
Yeah.
Would it be possible in that general setting, or a priori no?
Honestly, I don't know. This was I don't know. We tried a lot of things that in the end, that's what we arrived at that succeeded. But maybe there was a way to mix different approaches. We didn't do it that way because there is actually a lot of things that are quite sensible in this proof. But I can't answer really your question. Sorry.
No, that's okay. Don't worry. Thank you. Are there any other question? So, okay, if not, let's thank again Armand for this very nice talk.
Thank you very much.
So we will take maybe the 2 minutes just to switch speaker. So Thibault, would you try to share your screen and connect?
Yes, I will do it. Just a second. I think it's this one. Do you see it?
Yeah, it's
Yes.
okay.
Yes, perfect.
Okay, perfect.
Okay, so let's continue. And so the second speaker is Thibault Liard from LS2N in Nantes. He will speak about boundary sliding mode control of hyperbolic systems. Please.
Okay, so hello. Thank you for being here today. So As Sylvain said, I will talk about boundary sliding mode control of hyperbolic systems. And it's a joint work with Ismaël Balogun, Swan Marx, Vincent Perolaz, and Frank Plestin. 2 seconds. Okay, it works. So more precisely, I will consider a partial differential equations subject to an unknown disturbance. And the objective is to construct a boundary feedback law which globally stabilizes the input yi. So to that end, we will use a sliding mode strategy. Means that the sliding controller U is designed to attain a sliding surface infinite time. And on this sliding surface, the unknown disturbance is rejected and the global asymptotic stability is ensured. So the main question is for this strategy is how is the sliding surface constructed? In this presentation, the sliding surface is derived from the gradient of Lyapunov functions. So first of all, I will explain the strategy I will use, so the sliding mode strategy for ODEs. Then I will extend this strategy to linear PDEs, so it will be a linear hyperbolic PDEs, two hyperbolic PDEs. I will give some simulations, and I will end my presentation showing how the sliding mode control can be extended to non-linear PDEs, and in particular to scalar conservation laws. So first of all, I will consider the sliding mode control to ODEs, and I will explain the strategy I will use for PDEs. It will be very similar. So we consider the spring mass system with unknown disturbance D here. And x1 is the position of a solid, x2 is the velocity, m here is the mass of the solid, and k is the stiffness of the spring. So the control U is here and match with the disturbance. So the main question is, here is the equilibrium point 0 is exponentially stable. So when D is equal to 0, in general, it's classic to use this feedback control law, U dot T is equal minus U x2. And when you use this control law, we can prove that 0 is stable using the following Lyapunov function, which is the energy of the systems. And to prove that 0 is globally asymptotically stable, we can use the Lasage invariance principle. The main question here is what's happened when the disturbance D is different to 0. So in this case, we assume that we don't know the disturbance. We only know the L infinity bound of the disturbance. To reject the disturbance and to prove that 0 is globally asymptotically stable, with this, we will use a sliding mode strategy methods. As explained before, it's based on the constructions of a sliding surface and a sliding variables. A sliding surface is a set of x1, x2, such that sigma de x is equal to 0, and sigma is the sliding variables. So as I explained before, the sliding variables is constructed from the derivative of the Lyapunov functions. And the Lyapunov function is the one when the disturbance is equal to 0. So here we have V here when D is equal to 0. We compute the derivative of V, which is at the end equal to kx1 plus n x2. And thanks to this sliding variable, we can construct our sliding controller. The sliding controller is divided in two parts. The first part is this one, which is very close to this control without disturbance, except that V is replaced by K plus M. And we have a second terms, and this second terms is here to reject the unknown perturbation, the unknown disturbance. And we note that this sliding controller is a set-valued function because the sign here is a set-valued function. And if we assume that the gain of the control K here is greater than the L infinity bound of the disturbance, then we can prove that using this sliding control, 0 is globally asymptotically stable. So I will just give a sketch of the proof in this case, and I will use the same strategy for PDEs. So first of all, the main idea is to prove that the solution of these ODEs attains the sliding surface, sigma, infinite time, and remains on it. So to prove this, we will prove that the sliding variables, so it's sigma x1 x2 so we just replace here x1 and x2 by x1 x2 so you have just k x1 plus m x2 we can show that these variables is a Filipov solutions of this ODE. So here you have the disturbance, if you have the sign, if you have the gain, the k of the gain of the control. And I will encourage you that the Filipov solution of this ODE, it's an absolutely continuous map that satisfies this ODE for almost all t. And this, it's a set value function. So we just show that we just have to show that the derivative of sigma belongs to this set. And this is a classical ODE when we know some results about that. So it's very classic in this case. So if we assume that the disturbance belongs to n infinity and the gain k is greater than the n infinity bound of d, then we manage to prove that there exists a capital T. So there exists a time such that for any t greater than capital T, sigma de t, so the variable, the sliding variable at time t is equal to 0 for any t greater than capital T. This means, by definition of being a sliding surface, that the solutions x1, x2 belongs infinite time, so it's the time capital T, reach the sliding surface and remains on it. So here, I plot the sliding variables with respect to the time with different parameters. So here the disturbance is the sinus functions, k is equal to 2, the mass of the solid is equal to 1, and the stiffness of the spring is equal to 1. So we note that after t is equal to capital T, we have sigma de t is equal to 0. So sigma de t is equal to 0. So we reach the sliding surface here and we remain on it. So now we have proved that the solutions reach the sliding surface and remains on it. We have to prove that on the sliding surface, the solution is globally asymptotically stable. And how to prove that is just that on the sliding surface, the spring mass systems can be rewritten as the following system in blue. And we note that these systems in blue, it's exactly the same as these systems when d is equal to 0 and when we use this control. So we know that this system is asymptotically stable. So here I plot the solution in the plane phase, x1, x2. So at t is equal to 0, we are at -1, 3. So here we have the solution in the black line. And the blue line is the sliding surface. So we can see that the black line, the black curve is reaching the sliding surface and then remains on it and reach 0 when t tends to infinity. So now I will show how we can extend this sliding mode control to PDEs. So in recent years, some authors have applied the sliding mode control to PDEs. So I cite here some of them. And more precisely, I will consider the authors who work on linear hyperbolic systems with boundary input disturbances. Most of the case, to construct the sliding surface, the authors use a backstepping method. In our case, we will use more gradient of Lyapunov functions. And to prove existence and uniqueness of solutions, in most of the case, they use semigroup theory to prove that there exists a solution until a capital T, when the capital T is the time when the solution of the PDE reaches the sliding surface. And in our case, we will use a couple PDEs, ODEs to prove that the solution is defined in all times. So I will consider in this talk the following linear 2-2 hyperbolic systems. So I consider here the initial data belonging to LP. The first component of this system, so R1, has a speed lambda1 strictly positive, and the second component has a speed minus lambda2 strictly negative. The control match with the disturbance and acts on the first component of the system at x is equal to 0. And here K2 belongs to R. And we can see that this system is coupled via the boundary condition. So the objective here is to find a sliding surface on which the PDE here can be rewritten as the following one, infinite time capital T. And we have to impose that we have to choose K1 such that the absolute value of K1 and K2 is less than 1. And if we manage to prove that we reach this new PDE, systems, two linear systems, we can prove that from Bastin and Coron that 0 is exponentially stable for this PDE ODE. Donc, as the same as in the case of ODE, we will use a Lyapunov functions. So to prove that this systems is exponentially stable, from Coron and Bastin, they use a candidate Lyapunov functions, which is the following here. And our sliding mode strategy, which will be based on these candidate Lyapunov functions. More precisely, we consider the sliding variables as follows. So here it's the derivative in the certain sense of the Lyapunov functions. So we don't have square anymore here. And the coefficient P1 and P2 and nu, it's slightly different than the one used here, but the idea is the same. And now, since we have constructed the sliding variables, we can construct the sliding surface, which is a set of fg such that sigma de fg is equal to 0. And from that, we can construct the sliding controller, which is always divided by two parts. The first part is K1 R2T0, which is exactly this part. And the second one is minus K sine, the sign of the sliding variables, sorry. And this part is the set valued functions, which will reject the unknown disturbance. And we can see that K1 is chosen in this way. And we note that the absolute value of K1 and K2 is less than 1. So we can use these results later. So now I will state the main results of this presentation. So we consider the two linear hyperbolic systems with the SMC control and the unknown disturbance. So we only assume that the knowledge of the disturbance is the L infinity bound. We don't assume other things. So first of all, we have to prove that there exists at least one weak solution of these systems. So this is not it's not easy in general because we use a set valued function. And so we managed to prove this using a couple PDE-ODE I will explain later. And we proved that we have some stabilization results. That is to say, if we choose a gain K, so the gain is the gain of the control here, greater than the L infinity bound of the disturbance, we can prove that there exists a C and a mu such that for any initial data belonging to LP, we have the following inequality for any R1, R2 weak solution of this PDE. So to prove these results, we will prove firstly that there exists weak solution of this PDE. To that end, we introduce a new coupled PDE-ODE where the ODE is in blue here, and we can see that the ODE is not influenced by the PDE, but the PDE is influenced by the ODE at the boundary part, at the boundary side, so at x is equal to 0. So when K is greater than the L infinity bound here, so K is this value here, we know that for any gamma Filipov of these solutions, we have some properties, means that gamma dot plus nu gamma belongs to this set. And thanks to this information, we can prove that these systems, which is weak systems, we can prove that there exists a weak solution of these systems. And now the main idea is to prove that a weak solution of the coupled PDE-ODE is also a solution of a weak solution of the PDE. And to that end, we will use some kind of sliding variables, but compare with the other sliding variables, here S1 and S2 is the solution of the coupled PDE ODE. And thanks to this sliding variable, we can prove that the term here, gamma dot plus nu gamma, so the term at the right here, is equal to minus k, you sign the sigma dot t plus d dot t, which is exactly the term which appears in the PDE. So that's why the coupled PDE ODE is also a solution of the coupled PDE ODE is also a solution of the PDE. So it's how we prove that there exists weak solution of PDE without using, for instance, fixed point. So now we will prove, I will just give a sketch of how we can prove the stabilization results. So we assume that we have R1, R2, a weak solution of this PDE. And we introduce the sliding variables as in the case of ODE, which is sigma the R1, R2. So here R1, R2 is the solution of the PDE these times. And we can prove that the sliding variables is the Filipov solution of this ODE. And this ODE is exactly the same as the one I show you for in the ODE case. So with the same assumption, we have D belongs to L infinity and the gain of the control K is greater than the L infinity bound of D. We know that there exists a time capital T such that sigma dot T is equal to 0. Then the PDE can be rewritten as the following PDE, the following system of PDE. And with K1, this value, the absolute value of K1 and K2 is less than 1. And from Basta and Coron, this system is exponentially stable. So this approach can also work for non-uniform 2-2 hyperbolic systems. So means that the speed depends on the space. So lambda 1 and lambda 2 depend on the space x. In this case, we have to slightly adapt the sliding variables since the Lyapunov candidate, it's not the same. And we are confident that this also can be extended to an hyperbolic system non-uniform with source term, for instance. So now I will give some simulations to show the efficiency of this control. So first of all, we consider this system. So here there is no sliding mode control. It's just to show that the 0 is not globally asymptotically stable if we do nothing. So we have to act on these systems. So the first video here at the right, it's we plot the first component of the system at time capital T with respect to the x. And 0 here, it's the equilibrium point. So the initial, here we are t is equal to 0. We have t is equal to 0. So the initial time, the initial data is these functions. And here at the right, it's we plot the second component of the system. And this we have computed R1, and R2 using an upwind scheme. So I recall that they are coupled, these equations are coupled via the boundary condition. So we can see that this system is not globally asymptotically stable because of the disturbance. So now we will use the SMC as explained before. So sorry, I recall you that the parameter I use is this one, and the disturbance is the same as before, so it's the sinus function. And now we can see that here we act on at x is equal to 0 for the first component, and SMC here it's the value of the control. So we can see now we managed to reach the equilibrium point when t tends to infinity. And you can see the behavior of the control is very similar to the sinus function. And we have more is only knowing the L infinity bound of the disturbance this strategy may can reconstruct the disturbance even if we don't know the disturbance. So at the end, it's how it works. We manage to reconstruct the disturbance and we create a minus dt to reject the disturbance without knowing what kind of disturbance it is. So now I will try to explain how we can extend this sliding mode control to scalar conservation laws. So with entropy solution. So we consider the one-dimensional Burger's equations. So U is the solutions, F is the flux, which is U squared divided by 2. We control at x is equal to 0. So you have UL the t, it's the control, the left control, and UR the t is the right control. And the left control match with the unknown disturbance. The objective is to construct a boundary feedback law, UL and UR, which globally stabilizes the stationary entropy solutions, which is defined as follows. So here it's there is a discontinuity at x is equal to p. So here we have a shock. And as before, we have to define the sliding variables, the sliding surface, and the sliding controller. So in this case, we will use the we will use the following sliding variables. It's constructed in the following sense. The sliding variable is the difference between the mass of the solutions and the mass of the stationary entropy solutions. The left control is divided in two parts. The first part is the value of the stationary entropy at x is equal to 0. And the second part is the minus k sine the sigma. And this part is we need this part to reject the perturbation here. The second part is just y I at x is equal to L. And we don't need this term because we don't have disturbance at x is equal to L. But of course, if we want to extend this, we can also add a disturbance here. And in this case, we have to add a disturbance here. So now I will recall some properties linked to these equations. So first of all, there is non-regularity of solutions. That is to say, from smooth initial data, the solution can create discontinuities called shocks infinite times. So to define this solution all times, we need to introduce the Wick's formula. So more precisely, the function u is a Wick solution to this PDE if for any test functions, this equality is satisfied. A second barrier is there is an infinity of Wick solutions. So here I give two examples starting from a discontinuity at x is equal to 0. So in this case, this discontinuity can move or can dissipate, and both are Wick solutions. So to make this system well posed, a classical way is to introduce non-entropy conditions. More precisely, the function u is a Wick entropy solution if for any k and for any test function, this inequality is satisfied. The third barrier, because we consider boundary control, the third barrier is entropy boundary conditions. So more precisely, we have to define what is an admissible left side and what is an admissible right set, which is as defined as follow. So when we write in our system u the t0 is equal to u the L the t plus d the t, indeed, this means that u the t the 0 plus belongs to a set, and the same for the other side. So why this may be more complicated to deal with when you consider sliding mode control? It's because with entropy boundary conditions, the control may be inactive. I give here an example where the initial data is -1, the perturbation is the disturbance is equal to 0, u the L, so the left side is equal to 0.5 and the right side is equal to -1. So we can see here what is the solution. So at the end, the solution for any t is u is equal to -1. So u the LT is inactive because u the LT is different to u the t0 plus. So we have to deal with this type of problems, and we have more problems because of this. We have to deal with switching phenomena and delay phenomena and discontinuous functions. So if we consider the entropy, the stationary entropy solution yi defined as follows. So it's the shock at x is equal to p, and the control I explained before. We conjecture that for any u0 belonging to BV, there exists a finite time such that for any t greater than capital T, u de t is equal to the stationary entropy solutions, and u in the sense of entropy solutions. So you may have discontinuities in this case. To prove these results, so this it's a work in progress. We hope we will end this soon, so in a few months. So the first step is to using the conservation of mass to prove that the sliding variables, which as introduced at the first slide of this section, satisfy this ODE in the Filipov sense. And the main problem here is because of the entropy boundary condition, u de T0 plus and u de TL minus, we don't have that this is equal to the control. So because it belongs to a set. So we have to assume to add some hypothesis such that we have to find at a certain time, a finite time T1, the control at the right and at the left side is active. So using backward general characteristic, we can do this, and we can prove in particular that for any t greater than T1, u de T0 plus is equal to u de L plus d de T, and u de T de L minus is equal to u de R. And from this point, we can reproduce what we have done for ODEs and linear PDEs. In this case, we can show that gamma is a Filipov solution of this equation. And from this equation, we study it, and we can show that the sigma de t is equal to 0. So there exists a finite time t2, such that sigma de t is equal to 0 for any t greater than capital T2. And from this time, we can prove that u de t is equal to the entropy boundary conditions, because at the left side, we have the value of the stationary entropy solution at x is equal to 0. At the right side, we have the value of the stationary entropy solution at x is equal to L. And we know that the mass of the solution is the same as the mass of the stationary solutions. So with these three information, we have these results in red for any t greater than T2. So now I will give some simulation to show the efficiency of this method. So the solution is constructed using the Godunov scheme. So the first part is as before, so we don't control anything. So we just have the disturbance is sinus the t. Here it's here it's k, and this it's minus k. So in our case it's 1 and minus 1. So it is the stationary boundary, the stationary solution. The stationary entropy solution. So we want to reach this. This is the initial data here at t is equal to 0. And we can see that this solution doesn't reach the stationary entropy solutions. And when we control this with the sliding mode control here, so we have the same except this part. So here it's this value of the sliding mode control. We can see that this sliding mode control is very efficiency, and we can reach it very quickly, fast. It's fast, the stationary entropy solutions. And we can see that the SMC is reproducing the sinus function. So it's the opposite of the sinus function in this case, without knowing that it's a sinus function. So it works for any type of function where we know that the L infinity bound. So I will end my presentation with some conclusions. So in this presentation, I show you 3 different PDEs with boundary disturbances. So I study the linear 2-2 hyperbolic systems, the non-uniform 2-2 hyperbolic systems, and the scalar conservation laws, which is a work in progress. So I construct a boundary feedback law, which globally stabilizes a stationary solution without knowing the disturbances, but only knowing the L infinity bound of the disturbance. And to that end, I use a sliding mode strategy. So the sliding controller is designed to attain a sliding surface infinite time, and on which, on this sliding surface, the boundary disturbance D is rejected and the global asymptotic stability is ensured. And for the linear case, the linear PDE and the ODE, the sliding surface is derived from the gradient of the Lyapunov functions. So the main idea now is to extend this strategy to more general systems using, for instance, semi-group theory. And I would like to extend to systems of conservation laws with entropy solutions. So thank you for your attention.
So thank you, Thibault. Are there any questions? So if you have some question, please open your microphone and ask directly. So yeah, Jean-Michel, if you want.
Yes, it's a very nice talk. I was wondering if you construct a feedback law such that whatever is the disturbance, if it is less than K, then everything is good. But I was wondering if you have a Lyapunov function for the full system. You have the Lyapunov function for sigma, but for the full system, for the closed loop system.
In this case, we didn't manage to prove that we don't have, I will just show, for these systems, we didn't use Lyapunov function to prove that it's stable. So it's exponentially stable. So this is an open question and we are working on it. We don't know it. We just know how we can construct when we are on the sliding surface, but we use another strategy based on the method of characteristics. And for nonlinear case, it's backward general characteristics.
Yes, but the idea will be to understand if this is possible for the global when you are not on the surface.
I think it's possible. I think it's possible. Yes, we are trying to solve these problems, and I think it's possible, but we have still no clue how to do that.
Okay, thank you very much.
Okay, are there any other questions or comments? So, okay, if not, let's thank the speaker again. So thank you again, Thibault.